In the previous set of videos, we've given a detailed description of how the finite element method works, and then specifically applied that to the case of the 1D Helmholtz equation. So basically you could say, case closed, we know all there is to know. But what we're going to do in this video is approach this problem from a slightly different angle and see if this new point of view can give us extra insight into the advantages of the finite element method. So that's the goal of this video here. But before we arrive there, let's do a recap of some stuff that you know since the mists of time, right? So if you have a function f of x, it's basically a black box. You put in a certain number and out comes another number, right? And you can have a situation where you can minimize that function f of x. So if this is f of x over here and this is x, then there will be a certain value x star for which this function is minimized. And if that's the case, this basically means that in the neighborhood of that minimum here, the function really doesn't change a lot if you make some small variations around x for the minimum here. One way of expressing this is that the changes of f, expressed here by delta f, they are 0 around the location delta x for all possible changes that you can make, all possible changes around the x. So you can either make a change in the positive x direction or in the negative x direction, but that doesn't really matter. For all possible changes delta x you make in the input, the output will not change to first order simply because we're working in this extremum over here. Okay, so this is something you know, perhaps with slightly different notations over there. You can play the same game with a function that takes in 2 arguments for breakfast. So for example, 2 numbers, 1 and 2, and then it splits out a third number, 3 or 3.5 or whatever. Doesn't really matter. But also here you can play the optimization game, which is a bit more difficult to draw here. So let's say that there is a certain point x star y star where you have this 2D function. Let's try and draw this like this. Okay, it's really not very artistic, but I guess you get the picture. So at this location here, at this minimum, you will have the same situation where the function really doesn't vary a lot. So delta f is equal to 0 to first degree for all possible variations, for all possible changes that you can make if you run away from that optimal point x star, y star. So for all changes in x, but also for all changes in y that you can think of. Because we're working with the derivative here, we have the situation that the derivative is equal to 0. So the function itself, the output, doesn't really change to first order if you make some arbitrary changes in the input. Okay, so this is well known. These are functions. Let's now introduce a new beast, which is not a function, but a so-called functional. What is a function? What is the object that a functional eats for breakfast? Well, a functional does not operate on numbers as a function. Rather, a functional operates on functions. So as an input, we have a certain function f of x, which the function like this has a certain shape. And then as an output, it spits out another number, or whatever, or 3 or 4 or 5. So this is a functional. It's basically a structure which has an infinite dimensional input, right? Because in order to specify the input, in order to specify the function, you need to specify how it behaves at an infinite number of points. So it's, in essence, the infinite dimensional continuation of this, these multivariate functions here. So that's our new object, a functional. Question is, does this ring a bell? Do you remember from some of the previous videos a functional that we studied? So pause the video and see if you can remember what that functional was. Well, obviously, when we were trying to introduce the finite element method, we had this mysterious object J, which gave the total energy of the system, which is in essence a functional because it operates on the field. So if you have a certain field profile, psi of x, and then you calculate the energy, you end up with a number. So that indeed is the definition of a functional. So J of psi, the quantity that we introduced there, is a functional. Now, what's the next step here? If we follow the analogy here, we're going to try and minimize that functional. And if we do that, we're basically in the situation where we minimize a variational expression. So that's what we mean by a variational expression. It's looking for a certain function psi, such that the number that you get out of the functional, j of psi, such that that number is as small as possible. So it's minimized. Or another way of putting this, since we're looking at energy, so the energy that we get is the result of a minimization procedure over all possible functions psi of our functional j of psi. Okay. Now, if we try to draw a diagram like the ones we had up there, it's a little bit more complicated because this is an infinite dimensional input, and drawing infinite dimensional drawings is not really my strong suit. Drawing finite dimensional drawings is not a lot better, by the way, but okay. So let's try and draw this in a one-dimensional case. So let's assume that along the x-axis here, we have our infinite possible variations of our input psi. And then here we have the effects of j of psi. And let's assume here that this is just a 1D representation of an infinite dimensional space here on the horizontal axis. And again, we're looking for a certain psi, a certain function psi, such that this thing is minimized, and that gives us the energy here, early E. Okay. Question is, why on earth would this be useful or interesting to consider this from this particular point of view? So pause the video and try to think about this, and more specifically try to think about what happens when you have some sort of rounding errors or numerical precision errors, such that your numerical method doesn't really end up in the true point psi star here, but a little bit away from that. See how that affects the outputs of your functional. So pause the video and think about this. Now, since we're working with a variation expression, namely choosing the function psi such that our functional j is minimized, that also will mean, by analogy, that since we're working in that extremum, that small variations of psi will give rise to 0 variations of j. Just by looking at the analogy here we had delta f equal to 0, so variations in the output were equal to 0 for all possible variations in the input. The same is true here in the infinite dimensional case. Variations in the outputs are 0 to first order for all possible variations in the input that you can think of. And that's good news if you want to calculate the energy, because say you don't end up in the true minimum here, which would give you the real energy, but say you end up somewhere over here because you're working with finite precision or because you approximated your function with a finite number of unknowns. Say you end up over there. The consequence of the calculated value for the energy here is not really so big, simply because you're working in this minimum over here where the functional doesn't change, where delta j is equal to 0. So this means that if we're working like this, we're really much more insensitive to rounding errors, which would not be the case if you had a certain numerical method where you ended up over here, because in this particular case, if you make a numerical error and you end up over here, now the change here in the output is much bigger. So that's a huge advantage of these finite element methods, simply because they work on a variational principle, and that means then that they're insensitive to rounding errors. Now, that's true when you want to calculate the energy here of the system. Typically, calculating the energy is not really something that you're very interested in. But fear not, there's also other variation expressions which will give you, for example, the square of the propagation constant. And this is something that you could be very interested in. So if you have a numerical method like this, this will give you very good accuracy on calculating the propagation constant, even if you make rounding errors or other calculation errors on the input. Okay, so that's good news. A final thing I want to mention here is basically some terminology here and making sure that we dot the I's and cross the T's. So when we're solving this variational expression, when we're solving for psi such that we get a minimum of our functional, so that's basically a problem with infinite dimensions. And the way we're solving this in practice many times is by using the Rayleigh-Ritz method, which we've mentioned before already. And in the Rayleigh-Ritz method, we're going to say, rather than having this unknown function with an infinite number of degrees of freedom, we're going to approximate that with a finite expansion in basis functions. So we have a number of unknown quantities times known basis functions. But rather than looking at an infinite dimensional problem, now we're only looking at a finite number of unknowns. And then, Rayleigh-Ritz just takes the partial derivative of your function that you want to minimize with respect to all of the unknowns, puts it equal to 0, and then you have hopefully linear system. Now, strictly speaking, when you're doing Rayleigh-Ritz and when you're replacing psi with this finite sum of basis functions here, the resulting object will no longer be a functional, but it will be a normal function because it has a finite number of inputs. So when you write down something like this, it's still a functional because this here is an infinite dimensional object. But once you apply Rayleigh-Ritz and then you're calculating the energy, which then depends only on this finite number of unknown coefficients psi I, then you no longer are working with a functional, but with a regular, boring multivariate function. But that's just a small technical detail.